Okay guys, in our last video we took a look at what we mean by a complex number. In this video we're going to start our exploration of operations with complex numbers. And so a good place to start is just looking at what would have to be true about two complex numbers if they are equal. And so we're going to start with this definition of equality of complex numbers where it says given two complex numbers a plus bi and c plus di, we can say that a plus bi is equal to c plus di if and only if a is equal to c. So I'm going to underline this here. We say a is equal to c and b, not the I part, but just the b part, the coefficient of the imaginary unit, is equal to d. And so that is to say that when we have two complex numbers, what we're going to do is we're going to equate the real parts and we're going to equate the imaginary parts. In other words, these can only be the same number if their real parts are exactly the same and their imaginary parts are exactly the same. So typically what you tend to see are situations like this here where perhaps we know a complex number, say 3 plus 2i, and we say, hey, you know it's equal to this other complex number, x plus yi, and I'm really not sure what x and y are. I think it's fair to say then that because these are both written in standard form, we can go ahead and look at the real parts and set those equal to each other. We could say 3 is equal to x, and in this case just the coefficients of I, not the i's themselves, but we could say 2 is equal to y. And so if what we're looking for are x and y, well, you would see pretty quickly that we're done here. And the thing is, these are solutions to this particular equation. And when we talk about things being solutions, it just means that if we were to substitute these back in, we would have a valid statement. So you notice that if I were to take this x plus yi and substitute in 3 for x and 2 for y, we would get 3 plus 2i, and that is equal to 3 plus 2i. So taking a look at just a couple more examples here where we've got a couple of equal complex numbers, the trick is just to always equate your real parts. So in other words, x and 4 must be the same, and so x is 4. And then you equate your imaginary parts, which are the coefficients of I. So this means that our positive 6 here is actually equal to, we have to be careful, a negative y. And so in this case, we actually have to take it a step further. We'll divide both sides by a negative 1, and what we get as a positive y then is a negative 6. And just to go to show that this works here, we had x plus 6i equals 4 minus yi. If I take out my x and I take out my y and I make these substitutions again, negative 6 for y, and I suppose for x we had 4, we would see 4 plus 6i equals 4 minus a negative 6i, which really is the same as 4 plus a positive 6i. And so these would be equal. So for our last one, really quickly here, let's take a look at this. These two complex numbers in standard form. I notice that my real part here, 2x, would have to be the same as 8 if these numbers are equal. And just by dividing by 2, we get x is 4. And so the y part, I notice that I have a 3 here and a 4y is my coefficient here. And so we're going to say that this imaginary part equals negative 4y, the imaginary part on the right, and we would have to divide both sides by a negative 4. So this leads us to believe or to know that negative 3/4 must be the value of y. And if we were to plug these both back in for x and y respectively, we would get two equal complex numbers. So for the sake of equality of complex numbers, we want to know that just the real parts have to be equal to each other and the imaginary parts have to be equal to each other if these two numbers are equal.